Hello and welcome. Today we are beginning our journey into the history of atoms and how they shaped our universe. We will explore how elements were first forged in the cosmic furnace and how scientists slowly uncovered the secrets of the atom. This is not just a history of science, it is the history of everything around us, including ourselves. By the end of this lesson, you will see how we are truly connected to the stars. Let us get started. Today we have 4 specific learning targets. You will learn to identify and explain evidence supporting the Big Bang theory. We will also describe how this event formed light elements like hydrogen, helium, and lithium. Additionally, we will study the stages of star evolution and see how nuclear fusion powers stars and creates heavier elements. We will focus on the first essential question: how do stars act as cosmic furnaces to transform light elements into heavier ones? Take a moment to carefully think about how this concept connects to our everyday experiences with matter. Before we look at the stars, let us define our core field of study, which is chemistry. Chemistry is often called the central science because it connects physics, biology, geology, and medicine. At its core, chemistry is the study of matter, which is anything that has mass and occupies space. All matter is made of various combinations of atoms and elements. An element is a pure substance consisting of only one type of atom. The properties of matter depend on which elements are present and how their atoms are arranged. Let us look at some real-world examples. This diagram shows how central chemistry is to our daily lives. For example, in green energy, solar panels are composed of specially treated silicon. In biochemistry, the glowing light of a firefly results from a chemical reaction in the insect. In medicine, special plastics are used for medical tubing because they resist chemical attack. Finally, in technology, light-emitting diodes are made from elements like gallium and arsenic. Clearly, chemistry is all around us. Let us see where these elements originally came from. Where did all this matter come from? The Big Bang theory is the most widely accepted scientific explanation for the origin of our universe. It postulates that approximately 14 billion years ago, all matter existed as a hot, dense mass about 1 centimeter in diameter. This tiny point experienced a huge expansion, which is the rapid spreading out of space and matter. This event was accompanied by an emission of a huge amount of light, spreading a fast-moving cloud of gas. Let us examine the timeline of this expansion. This timeline shows how the universe changed as it expanded and cooled. At time 0, the universe was a point sphere of infinite density. Within 1 second, the temperature dropped to 10 billion degrees Celsius, allowing protons and neutrons to form. A proton is a positively charged subatomic particle. Between 1.5 and 10 minutes, helium and deuterium nuclei formed. Finally, after 300,000 years, the first neutral atoms appeared. Let us see how scientists developed this theory. How do we know the Big Bang actually happened? There are several strong lines of evidence. First is cosmic expansion, discovered in 1929. Second is the cosmic microwave background radiation, which is the leftover heat from the early universe. Let us review these pieces of evidence. To understand how the universe expands, we can use the analogy of an expanding balloon. Imagine coins taped to the surface of a balloon. As you inflate the balloon, the coins move farther apart from each other. In the same way, galaxies recede from each other as space itself stretches. This stretching of space causes cosmological redshift, which is the stretching of light waves as space expands. Let us look at a real astronomical image of this phenomenon. This deep space image shows many distant galaxies. Astronomers observe cosmological redshift in the light coming from these objects. Cosmological redshift is the stretching of light waves as space expands. Light from sufficiently distant sources shows a redshift that corresponds directly to how fast they are moving away from Earth. A simple analogy is the changing pitch of a police siren as it drives away from you. This observation is key evidence that the universe is expanding. Let us move to our second line of evidence. Our second major piece of evidence is the cosmic microwave background radiation, or CMBR. This is the faint heat left over from the early universe. This radiation reveals tiny fluctuations, which are small differences in the density of matter when the first atoms formed. Gravity worked on these density ripples over billions of years, pulling matter together into clumps. These clumps eventually became the galaxies and superclusters we see today. Let us look at a detailed map of this radiation. This vibrant map is a baby picture of our universe, captured by a space probe. It shows the cosmic microwave background radiation, which is faint heat radiation left over from the early universe. The different colors represent minute temperature fluctuations. These tiny differences in heat correspond to variations in the density of matter. Over billions of years, gravity pulled matter toward the denser areas, forming the galaxies we see today. For example, these blue and red spots are the cosmic seeds of our own Milky Way galaxy. Have you ever wondered why the night sky is dark? In 1823, Heinrich Olbers pointed out a paradox, which is a statement that seems self-contradictory but is true. He argued that if the universe were infinite in size and age, the sky should be completely bright with starlight. The fact that the sky is dark proves that the universe is not infinitely old. Because the universe had a beginning, we can only see light from stars that are close enough for their light to reach us. To understand how light stretches as the universe expands, we must look at the electromagnetic spectrum. Electromagnetic radiation is energy that travels and spreads out as it goes. This chart shows the different types of radiation, from long radio waves and microwaves to short, energetic gamma rays. Visible light is only a very tiny portion of this entire spectrum. For example, we use microwaves every day to cook food, while doctors use X-rays to view inside our bodies. Let us examine how this connects to gravity. Our fourth major line of evidence comes from the field of theoretical physics. In 1915, Albert Einstein published his general theory of relativity. This theory describes spacetime, which is a mathematical model combining space with time. Einstein's equations revealed a startling truth. The universe cannot remain stationary. It must be either expanding or contracting. This theoretical prediction laid the groundwork for the Big Bang model. Now we look at one of the most famous equations in all of science, E equals mc squared, which comes from the theory of special relativity by Albert Einstein. This formula describes mass-energy equivalence. We define mass-energy equivalence as mass and energy being interchangeable. The letter c represents the speed of light, which is an incredibly large number. Because we square this speed, even a microscopic speck of matter holds a massive amount of locked-up energy. For example, a single gram of matter contains enough energy to power thousands of homes for an entire year. Without this equation, we cannot explain how stars shine or how nuclear power plants generate electricity. Einstein's journey to general relativity began with the equivalence principle. This principle states that gravity and acceleration produce identical physical effects for an observer. As you can see in the diagram, an observer in a rocket accelerating at 9.8 meters per second squared feels the exact same downward pull as an observer standing on Earth. This realization led Einstein to conclude that gravity is not a traditional force, but rather a bending of spacetime. Let us look at how mass causes this bending. According to general relativity, mass tells spacetime how to curve, and curved spacetime tells mass how to move. Spacetime is the four-dimensional fabric that weaves space and time together. Massive objects like our sun warp this fabric, causing the paths of traveling objects and even beams of light to bend. This is shown in the diagram where starlight bends as it passes near the sun. Because of this dynamic warping, the universe cannot be static. It must expand or contract. This slide illustrates how gravity shapes the ultimate fate of our universe. General relativity describes spacetime, which is the physical fabric of space and time. Depending on how much mass is in the universe, we face three possible ends. We could experience a big crunch, where gravity pulls everything back into a single point. Alternatively, we could face a big freeze, where everything drifts apart and cools down. For example, a campfire eventually burns out and grows cold when its wood is completely consumed. We will now look at our final major piece of evidence, which is the balance of elements in our universe. When scientists write out the nuclear equations for the first few minutes of cosmic history, the math predicts a very specific outcome. It predicts that 3/4 of all ordinary matter should be hydrogen and 1/4 should be helium. When astronomers measure the actual gas clouds in deep space today, they find this exact 3-to-1 ratio. The calculations perfectly match reality. Now let us transition from the cosmic scale to the atomic scale. To understand how elements formed, we must review atomic structure. An atom consists of protons, neutrons, and electrons. The center of the atom is the nucleus, which is a tiny and dense region at the center. Protons determine the atomic number, represented by the letter Z. Neutrons and protons together determine the mass number, represented by the letter A. An isotope is an atom with a different number of neutrons. For example, carbon-12 has 6 protons and 6 neutrons. This timeline shows how the balance of elements began in the early universe. Scientists calculate that just seconds after the Big Bang, the universe was filled with high-energy photons. A photon is a tiny particle of electromagnetic radiation. Within the first 4 seconds, some photons formed protons, neutrons, and electrons. By the time the universe was 3 minutes old, these protons combined to form deuterium and helium nuclei. Let us look at the reactions that made this possible. To understand element formation, we must define 2 types of nuclear reactions. Nuclear reactions are processes that change the nucleus of an atom. First is nuclear fusion, which combines light nuclei into heavier ones and powers stars. Its examples are nucleosynthesis, or the creation of new atomic nuclei, and thermonuclear reaction, which refers to a high-temperature nuclear reaction that happens in stars and hydrogen bombs. The second type of nuclear reaction is nuclear fission, which splits heavy nuclei into lighter ones. Its example is radioactive decay, where unstable nuclei lose energy by emitting radiation. Over time, they transform into more stable atoms by releasing particles such as alpha particles, beta particles, or gamma rays. Let us study this comprehensive table of nuclear reactions. First, alpha decay occurs when an unstable nucleus emits a helium nucleus, which reduces the mass number by 4. Second, beta decay occurs when a neutron turns into a proton, emitting a high-speed electron called a beta particle. Third, gamma emission is the release of a gamma ray, which is high-energy electromagnetic radiation. This table also shows positron emission, electron capture, and alpha bombardment, where a nucleus is hit by an alpha particle. An everyday example is how smoke detectors use alpha decay to detect tiny smoke particles in the air. Let us practice balancing nuclear equations with these first two examples. In reaction 1, radium-226 decays into radon-222. To balance the mass and atomic numbers, we need a particle with a mass of 4 and charge of 2. This is an alpha particle, indicating alpha decay. In reaction 2, europium-159 decays into gadolinium-159. This process requires a beta particle, indicating beta decay. Big Bang nucleosynthesis refers to the creation of light atomic nuclei during the early universe. This slide shows the specific nuclear equations that occurred when the universe was only 100 seconds old. During this brief period, protons and neutrons combined to form deuterium, tritium, helium, and lithium. Astronomers observe a mass ratio of hydrogen to helium of 3:1 in deep space today, which perfectly matches these nuclear equations. This slide highlights a critical turning point in cosmic history. When the universe was 30 minutes old, it had cooled so much that nuclear reactions stopped. Then, at 400,000 years old, the universe was cool enough for helium and hydrogen nuclei to capture electrons and become neutral atoms. At this point, photons could move freely, and gravity began pulling matter together to form the very first galaxies. This slide introduces stellar formation and evolution. Over millions of years, gravity pulled hydrogen and helium gases together to form stars. As these stars contracted, they became hotter and denser, starting nuclear reactions that produced elements heavier than lithium. This process allowed light elements to combine, creating carbon, neon, oxygen, silicon, and iron. Let us examine the structures where this star birth takes place. This slide showcases 3 famous images of stellar nurseries captured by telescopes. The Pillars of Creation, the Christmas Tree Cluster, and the Eagle Nebula are giant clouds of interstellar gas and dust. These clouds combine visible and infrared light to show where young stars are actively forming. The dense regions in these clouds contain cold dust, where gravity is slowly pulling matter together. Let us see how these stars generate energy once they form. Thermonuclear reactions are nuclear fusion processes that occur at extremely high temperatures. These reactions are the engine of stars, powering them throughout their lifetimes. This diagram shows the life cycle of a sun-like star. It begins as a hydrogen-burning core, then expands into a red giant star as hydrogen is depleted. The reactions that form new elements happen in concentric regions called fusion shells. Let us see what elements form in these shells. This cross-section shows the onion skin structure of a highly evolved star. As the star ages, heavier elements are produced in concentric fusion shells, increasing the density toward the center. This nucleosynthesis chain starts with hydrogen and helium and proceeds through carbon, oxygen, neon, silicon, and finally cobalt and iron. However, the production of elements stops when iron-56 is formed because fusing iron requires an input of energy. When a massive star runs out of nuclear fuel, its core collapses under gravity, triggering a spectacular stellar explosion called a supernova. A supernova is a violent explosion of a dying massive star. This incredible event releases a massive amount of nuclear energy. Under these extreme conditions, elements heavier than iron are produced through neutron capture. Neutron capture is a nuclear reaction where a nucleus gains a neutron. These newly formed elements are then scattered into deep space to form new planets. This slide compares 2 pathways for building heavy isotopes during a stellar explosion. An isotope is an atom with a different number of neutrons. The first pathway is the R process, which is rapid neutron capture occurring before beta decay can happen. This process produces heavy elements, like cobalt from iron. The second pathway is the S process, which is slow neutron capture occurring after beta decay has happened. This slow process produces elements like copper and zinc from nickel. Let us look at another crucial high-temperature process called photodisintegration. During the late stages of a star's life or during a supernova, high-energy gamma-ray photons strike nuclei and effectively break them apart. As shown in the diagram, a silicon-28 nucleus is broken down into 7 helium-4 nuclei, which are also known as alpha particles. Other nearby nuclei then capture these free alpha particles. This sequence of additions is called the alpha process. It allows the star to quickly build heavier, stable isotopes like sulfur-32, argon-36, calcium-40, titanium-44, chromium-48, iron-52, and nickel-56. This graph displays the abundance of chemical elements in our solar system, plotted against their atomic number. Notice that hydrogen and helium are by far the most common, as they were created in the Big Bang. The next 3 elements are rare because they are poorly synthesized. For heavier elements, we see a general decrease in abundance as mass increases, and an alternation where even atomic numbers are more common. This colorful periodic table from NASA shows where each element was born. A periodic table is a chart organizing elements by their repeating chemical properties. Hydrogen and helium were created during the Big Bang. Elements like carbon and oxygen were formed by dying low-mass stars. Heavier elements like gold were produced by merging neutron stars or supernovae. This chart shows how closely connected we are to the history of the cosmos. To close our exploration of stellar chemistry, let us consider this iconic quote from Carl Sagan. Sagan possessed a wonderful ability to explain science in a poetic and deeply meaningful way. He explains that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pies were all made in the interiors of collapsing stars. Because these stars exploded billions of years ago and dispersed their elements across space, we are literally made of star stuff. It is a powerful reminder of how we are connected to the history of the universe. Let us summarize the key takeaways from our lesson today. First, we reviewed the 5 lines of scientific evidence that support the Big Bang theory, including redshift, background radiation, general relativity, element abundances, and Olber's paradox. Second, we examined how the Big Bang model explains early matter formation through various nuclear reactions. Finally, we learned that elements were forged in 3 distinct cosmic stages. Lighter elements formed in Big Bang nucleosynthesis, elements from beryllium to iron formed in stellar cores, and elements heavier than iron formed during stellar explosions. We can now resolve our first essential question. Stars act as cosmic furnaces by fusing light elements like hydrogen into heavier ones, such as helium, carbon, and oxygen in their cores. As stars evolve, particularly during explosive events like supernovae, they create even heavier elements and disperse them throughout the universe to form new planetary systems. To complete our lesson, here is your exit ticket pop quiz. You should be able to answer 3 questions. First, name 1 element formed in the Big Bang. Second, write a fusion reaction that occurs in stars, such as hydrogen fusing into helium. Third, explain how elements heavier than iron are formed. Please write your answers on a sheet of paper before leaving.